Let's take a look at some of our other types of radiation. We've talked a lot about UV electromagnetic radiation. We talked about the difference between non-ionizing and ionizing radiation. So we talked about our DNA damage. However, we haven't talked about some of our lower energy radiations, such as microwaves, infrared. We know what UV light does. It removes electrons, it breaks chemical bonds. So do these. So let's take a look at how infrared interacts with molecules. Because this is not high enough energy to break chemical bonds, it does something else. So this is, IR radiation is energy, yes. All of this, everything we're talking about is electromagnetic radiation. And it is energy. So this energy, when it hits molecules, it does things to them. It interacts with them. And so one thing that IR radiation does is it's not strong enough to remove electrons and break chemical bonds, but what it does do is it causes them to vibrate. It is strong enough to cause that to happen. So what it does is it actually gets inside the molecules and it bounces around inside of the molecules. And we're seeing them expand and move around. I'll show you how this works. So this is kind of what it does to your atoms. It can cause them to vibrate this way. Sometimes it can cause them to vibrate this way. Sometimes it can cause all of these things to vibrate. But essentially, the energy getting inside of it is causing it to do this. Now, some of our less harmful radiations, such as microwaves, these are things that we commonly encounter in our day-to-day life. These are produced by things like our mobile phones, your wireless router, radio, and these orient molecules. So they don't have enough energy to cause them to vibrate. They aren't high enough energy to do that. But what they do is they pull on molecules. So what this does is it causes them kind of to line up. So a molecule might just be kind of floating about. And then when it encounters a microwave kind of helps orient it a specific way and it fixes it in a specific way. If you move the microwave, the molecule might follow the microwave as well. So this type of electromagnetic radiation causes rotation and orientation. Here's an example of this. So let's talk about, say, an electric field. This is a type of electromagnetic radiation that's in our microwave spectrum. So when we have a positive voltage, you might see this here is most likely water molecules. And what we see here is that our partially negative charge of the oxygen here, this is our oxygen, so our partially negative charge is lined up to the positive, and positive's on the opposite side. When we have a negative, we're going to see the positive side, our hydrogens, are going to be closer to the wave. And you can see this as the field alternates between positive and negative voltage. Here's an example that might make a little bit more sense. So in an unpolarized area where there's no microwaves, you can see that molecules tend to just float around like this. They're just floating around. They might be oriented anyway. But when you put an electric field on it, when you have a positive on one side and a negative on the other side, all of the molecules orient themselves so that the negative is pointed towards the positive and that the positive is pointed towards the negative. They all line up like this. And this is how microwaves interact with our molecules. So in summary, here's kind of how all of these different types of radiation interact with molecules. So our ionizing radiation with UV and things higher energy than UV, like X-rays and gamma rays, break molecules. They break molecules by removing electrons. They're high enough energy to just hit a molecule and just cut it apart. Our infrared light in this range is not high enough energy to cut molecules apart, but it is high enough energy to get in the molecule and make it dance. It will excite it, it vibrates it, it causes it to stretch and move in different directions. And then our microwaves are not high enough energy to get inside the molecule, but what they can do is they can kind of orient the molecule. So it might be floating in space, and our microwaves can cause it to line up in a specific fashion and cause it to orient in the way that you want it to. So our microwaves can rotate molecules or orient them. Let's talk about an application of this electromagnetic radiation, how it interacts with molecules. One of these is the greenhouse effect and what we call greenhouse gases. So this has everything to do with electromagnetic radiation hitting molecules in our atmosphere and interacting with them. So we talked about how ozone protects our Earth, but let's talk about how things like carbon dioxide warm our Earth. So when energy comes off the sun, it comes into our atmosphere, and some of that light is reflected, some of it is trapped by ozone, and some of it is trapped by things like carbon dioxide. Let's see how this molecule absorbs heat from the sun. So the type of electromagnetic radiation that causes global warming is our infrared. So our ionizing radiation is absorbed in our ozone layer. That's where our ionizing radiation from the sun goes. Now our infrared is not absorbed from the ozone layer, it goes through, and it's absorbed by other things in our atmosphere. So infrared in particular has just the right frequency to be caught and trapped by molecules and cause them to vibrate. So essentially what's going on is that this energy comes in, it hits things like CO2, and it causes them to vibrate. And that's how the energy gets trapped, because it's inside the molecule. Every molecule, like CO2, methane is also a greenhouse gas, has a unique vibrational pattern. So the way that it vibrates, does it stretch this way, does it stretch this way, does it stretch all around like this, is determined by the shape of the molecule and its electron distribution. We aren't really going to go into that, but do know that each molecule absorbs a specific frequency of electromagnetic radiation. So these greenhouse gases, like these types of molecules in our atmosphere, become sinks because they trap the IR radiation coming off the sun inside of them. It's stuck inside. So let's take a look at how this works. So here's a vibrating, this is actually ammonium. You can see it stretching like this. And when you hit this with electromagnetic radiation, it can cause this to happen more. And the reason that this happens is through this thing called constructive interference. So when you have an electromagnetic wave interact with the frequency of the molecule, so let's say this is your EMR, and this is your molecule frequency. Now you might not think of molecules as having a frequency, but we can see here, we can see this molecule expanding. It does have a frequency. It's doing this so many times per second, which means that that is an energy that's oscillating. And electromagnetic waves are oscillating energy as well. When you have these two frequencies interact with each other, these two waves interact with each other, when they happen to be the same frequency, what happens is these things build. They cause this thing called constructive interference, and the magnitude of the wave gets bigger. So it's kind of like additive. So these add up, and you can see now that this wave is taller. The amplitude of it is higher. So what might happen is if you had constructive interference from electromagnetic radiation hitting this ammonium molecule here, you might see that the distance at which these atoms expand increases. So now, instead of going to the regular length, they go even further because it's got more energy to do so. The opposite of this is destructive interference. Destructive interference is when you have one frequency, say of your electromagnetic radiation, and it hits the molecule frequency and they aren't the same. Sometimes the waves can destroy each other, and you see that they don't add up like this. So this is a very special circumstance. When both of our waves have the same frequency. The way that I like to think of it is I like to think of it as like double dutch and jump rope. So you know how like you have somebody turning the rope for you and you've got to jump into the rope? It's kind of the same thing. That rope has a frequency. It's hitting the ground 1, 2, 3, 4, 5 times, right? And you have to have the exact same frequency to get in there. You have to jump at that same pace, or otherwise you're not going to be able to enter the jump rope. It's the same thing with a molecule. A molecule has that same frequency, 1, 2, 3, 4, 5. And for that electromagnetic radiation to get inside that molecule and interact with it, it has to have the same frequency. It has to jump with it at the same pace. And so that's what's happening here with our electromagnetic radiation and our molecules. That's why they vibrate, is because they're literally getting inside of the molecules, which helps them hold on to that energy, which causes that energy to heat up our atmosphere and cause things like greenhouse gases to warm up the Earth. So here's a preview to our next topic. I just kind of want to connect this one to the next. If you think about what makes a gas molecule a greenhouse gas, we only have specific gas molecules that are greenhouse gases. So our carbon dioxide is a greenhouse gas, methane is, our ozone, things like nitrous oxide are actually floating around the atmosphere. Water vapor is a greenhouse gas. These are all molecules here that can absorb IR radiation from the sun. But our nitrogen gas and our oxygen gas don't do this. They don't absorb IR radiation from the sun. So what causes a molecule, some molecules to be able to do this and other ones not? So the reason this happens is because this is determined by the molecular shape in the atoms inside of the molecules. So specific things like the charges on these atoms allow it to have a specific frequency. So we're going to talk about something called dipoles in the next chapter. So a net change in dipole moment during a molecular vibration is what causes it to be able to absorb certain frequencies of electromagnetic radiation. So this is a preview to topic 7. Because in topic 7, we're going to be talking about dipole moments and how to find them and how to understand why some of these molecules here have dipole moments and these don't. And why that causes these to be able to have a certain molecular frequency and these don't. These can't absorb IR. But these do. Okay, so that's it for topic 6.